Hello everyone, welcome to my YouTube channel. We are starting a series of lecture on this YouTube channel, and in this series we will be solving some of the complicated physics problem. The problems will be mostly useful to you if you are preparing for JEE mains or advanced or NEET exams. So let's start. So here is the problem which we are going to solve. This is a pulley with a spring system attached to a fixed hook, let's say ceiling, right? So in the equilibrium position, there will be some extension or some stretch in the string, and then this will be in the equilibrium. If you pull the pulley slightly down, there will be oscillation, right? So if you pull it with a small distance x, this will start moving into vertical direction in the simple harmonic motion. So what we need to find out is what will be the natural elongation of the string when the system is in equilibrium. That's the first problem statement. Second problem statement is, let's say if we pull it down and then this goes into a simple harmonic motion, what will be the time period of this pulley? And assumption is string and the spring both are light, massless, and then friction between the pulley and the string is such that there is a pure rolling motion. Okay, so we will be solving this problem with two approaches or two alternative way we will be solving the problem. One way is by the principle of conservation of energy, and the second way we will be solving this problem by applying the Newton's law of motion. Okay, so let's start with first approach. Uh, okay, solution. Solution 1. What is the solution? This solution is by principle of conservation of energy. Okay, now let's see the system. Uh, What happens if this pulley goes down by a distance of x? If you see it carefully, this part and this part both will go down by a distance of x, right? And since this string, they know this string is not stretchable, we can assume that only stretch will happen is in the spring. So if this pulley go down by x, the spring will get extended by or stretched by 2x. Just remember that. That's one concept. Now second point is, since this system is in equilibrium, so both linear motion in the y direction and rotational motion about the center of the pulley is zero because there is no moment. It means it has to be balanced. Okay, so I have drawn the free body diagram of the pulley. See, let's see the tension in the string is T. So this is how this vertical forces will look like. And assume that in the equilibrium position, the normal uh, stretch or extension the spring is x naught, right? Just assume that. Now for this equilibrium position in the vertical direction, let's first write this x naught equal to uh, extension in the spring at vertical equilibrium, at equilibrium basically, right? So for pulley vertical equilibrium 2t equal to mg, This means T equal to mg by 2. Since spring is massless, so the re since spring is massless, the force developed, the restoring force developed in the spring will be equal to the tension, right? So if you draw the FBD, free body diagram of a spring, how will this look like? Let's see like this. So there will be a restoring force, right? And if x naught is an extension in the spring, it will be kx naught upward, and then T is downward. This means T equal to kx naught, right? Or let's say this is equation number 1, and then this is equation number 2. So x naught will become T by k, and from equation 1 and 2, what will happen? X naught equal to, put the value of k, it means mg by 2k. So this is the natural extension in the spring when this pulley is in the equilibrium position, right? Now, what is being asked here is, let's say if this system is slightly displaced downward, right? What will happen? What will happen to the system? Guess it. It's going to be in the SHM, simple harmonic motion. Okay. So let's what we'll have to do is we'll have to prove that this is going to be in simple harmonic motion, and if this is the case, what will be the oscillation in the spring system or this pulley system? So we need to find out the time period of oscillation. Okay, so uh, let's assume let us assume the pulley is pulled down by x. So what will be the extension in the spring? Extension will be 2x, right? Because this body will go down, something like, you just see like this. Let me draw some diagram. You are right now here, right? Now let's say it is pulled down by a distance of x, right? So this part of the string is also is stretched by x, and this part of the string is also stretched by x. It means total elongation in the string will be 2x. And from where this 2x will come? This elongation will come from the spring, because string is non-stretchable. So uh, is total stretch in the spring will be, tell me how much? The initial stretch, which was x naught, plus this 2x, right? And potential energy of a string will be half kx square, right? So half kx square, x naught plus 2x whole square, right? This is what? This is increase in the potential energy, right? Because we stretched it. Someone applied the force to stretch it. The work done by that force is stored as the potential energy of the string. What will be the uh, what will be the potential energy change in the pulley because it is pulled down by x. So since it is being pulled down, there will be a decrease. There will be a decrease in the potential energy of the pulley, right? PE of pulley equal to M, or let's say capital M G X. And this is what? This is decrease, right? Now, what are the other energies here? Since this body is also having a vertical velocity, right? Since it is oscillating, right? So there will be a vertical velocity, and then there will be a rotational motion also because string is not slipping over the pulley. So it's a case of pure rolling motion, right? So kinetic energy of the pulley equal to, what do you know? Half I omega square, right? And then this is rotational kinetic energy, and then there is a half mv square. This is linear kinetic energy, right? And omega, what do you know? Omega equal to v by r. So put this value here. So what will become? K will become half I v square by r square, right? Plus half mv square. Now, one thing I missed. This energy is what? This is increased because initially the system was at rest and now the system is in motion. So this kinetic energy initially was zero and now you have this positive kinetic energy. So since the total energy of the system is conserved, why conserved? Because this is a all these forces are conservative forces. Whatever forces are working in the system, the let's say the spring force, the gravitational force, these are all conservative forces. So total energy of the system will remain constant. What does it mean? It means decrease in potential energy will convert into the increase in potential energy plus kinetic energy. It means mgx, which is decrease in potential energy, is equal to half k x square plus 2x whole square, right? And then plus half I v square by r square plus half mv square, right? Okay. So what we can do to solve this problem is we can use differential calculus. Let's apply the differentiation here. So differentiating each side with respect to time, what you will get? D by dt mgx equal to d by dt half k x square plus 2x naught into x, sorry, this is not 2, differentiating. Now let's differentiate with respect to time at both sides. So what you will get? plus 2x naught into 2x plus 4x square plus iv square by 2r square plus mv square by 2. Right? Now this is just a plain calculus. If you differentiate it with respect to time, this will become mg, which is a constant, dx by dt equal to, let's take out half k, and then since x naught is a constant, it will become 0 plus 2x naught into 2x, which is dx by dt, plus 4 into 2x into dx by dt. This is plain differentiation. Then iv square by 2r square will become I by 2r square 2v into dv by dt plus m by 2 2v into dv by dt. We know that acceleration a equal to dv by dt and velocity v equal to dx by dt, right? So if you put this value, what it will become is mg v equal to k by 2 2x naught. We'll put the value of x naught. What is the value of x naught is x naught mg by 2k. See here. So if you put mg by 2k, 2 into mg by 2k into 2 and ds by dt is v plus 4 into 2 8 xv plus, let's solve the second problem. This 2 and this 2 we can cut. So it will become v by r square and dv by dt nothing but a plus again this 2 and this 2 we can cut mv a, which is dv by dt. Now let's solve this quickly. 2 2 you can cut out, right? So it will become mgv, then k by 2 and mg into 2v. This 2 and this 2 will cut, so it will become, and this k will also cut out. So it will become mgv plus 4kxv plus v by r square plus m mv, and let's take a common. You can see this mgv and this mgv will cut out. What it will become is, just keep this term here and this term let's bring to the left. This will become v1. I think we missed one part is, this is not 1, this is I, which is moment of inertia, right? So we just missed this part. We treated this 1, right? So this is big I. Now you could take I by r square common. This will become m a rho minus 4k xv. Since v is there in both sides, you can cut it. This becomes a equal to minus 4k by I by r square plus m, and then times x, right? What is this? You can represent this in like this: a equal to minus omega square x, where omega square equal to 4k by I by r square plus m. So this is nothing but equation of SHM, simple harmonic motion, where the omega is given by this. So this proves that this is SHM, right? And time period t is equal to 2 pi by omega, which is nothing but 2 pi by under root I by r square plus m by 4k. So this is the time period of the simple harmonic motion. What did we learn here? Let's just do a recap. Recap is we are given a system like this, and this system is in equilibrium. If we move this pulley down a little bit, then this system will start oscillating into simple harmonic motion, right? And then we solved this problem by the principle of conservation of energy, which is method 1, right? And with this, we proved that this is a motion of simple harmonic motion, and we were able to find out the time period. So that's it for now. In the second video, I'll be solving this problem by applying everywhere Newton's law of motion.